Well, let's get into it. This would be a section 2.6 if we're in the Stewart text still. Maybe we're in another text now. Who knows? Maybe we're in the future. Hey, if you know what a horizontal asymptote is from a rational function, you already know this game, you can just skip this one. I'm not going to put any quizzes or any bullshit in this. This is just a review of horizontal asymptotes, which is going to make finding these limits in infinity just cake. You'll kind of, well, not all of them, but it makes it a lot easier. Let's go. So it's a review. All right, here we go. See, review. Degree of a function? What's that mean? What's the degree of a function? We got to make sure we're all speaking the same language here. So the degree of a function, that's just the greatest exponent, whatever that number might be. So we're just quickly going through this. This is all algebra review. So we look at our first one and we go, what's the degree? What is the degree of f? And you just look through the exponents and go, what's the biggest freaking number? And you're like, 3. It's degree 3. Cool. Let's go to our next. What's the biggest exponent? Where do we got it? What's going on? That's 4. 4 is the biggest. So 4. We write that down. There's his degree. Let's go to our next. We got h of x. And we're like, what's the degree? What's the biggest exponent? We're like, well, shit, it's that 5 that's right there, huh? So our degree is 5. Now we move to our next. And we're like, well, what's j of x? What are we getting here? What are we getting there? And we're like, oh, shit. I don't know. What's that? That weirdo was saying something about the square root is x to the 1/2, right? That 1/2. So I guess the degree of that's 1/2. Cool. All right, well, let's go to p of x. Let's take a look at this one. What's that pi doing out there? That's a number. Like, nobody was tripping on that 7, right? Or the 1. Pi's just a number. Who gives a shit about that? Don't even look at that. So we're like, what's the biggest number? 7, 22 over 3, or 1? Well, 22 over 3 is actually the biggest number. Because 21 over 3 is 7. So, hey, there's the degree. Quick little review. Sweet. Moving on. Now, we start to get into the weird. This is what we call a rational function. A rational function. You messed around with it if you were in college algebra or pre-calculus, for sure you messed around with rational functions, and this was probably some of the biggest pains in the asses you had to deal with. At least for graphing, I know, because I teach college algebra and pre-calculus, or taught, and I know my students get a little sad, and they don't perform all that well. So let's discuss. A rational function. A rational function is just essentially a fraction. It means you got a polynomial over another polynomial, or just some sort of function over a function. Let's just call it that. It should be a polynomial, but my words aren't technically proper here. But you got some sort of function over a function, and I just want to talk nothing more than just the degrees of the functions. So let's say, for example, r of x equals x squared minus 4 over x cubed plus x minus 7. And I ask you, what's the degree of the top? And you're like, 2. What's the degree of the bottom? 3. Cool? Cool. Cool. Let's talk about horizontal asymptotes. Horizontal asymptotes. Shit that does things like this. Oh, but horizontally just gets closer and closer and closer, but it doesn't actually touch it. You know those horizontal asymptotes? So make sure we're speaking the same language, right? Horizontal asymptotes. Look at that. We have one right here. And as far as my graph is saying, we have one at y equals 0. That's where it's at. Because getting closer and closer to that x-axis. That x-axis is y equals 0. It's kind of weird, huh? The x-axis is where y equals 0. The y-axis is where x equals 0. So we have a horizontal asymptote at y equals 0. Now, we can have them all over the place. They could be at any number. But you might be looking up here and going, well, what's this? Well, from like a college algebra class, we could look at this first one and say, well, hey, we learned that if the degree of the top is larger than the degree of the bottom, we're not going to have a horizontal asymptote. It's actually going to blow up. So that's not this case, right? That's not the case we just did. That's a different case, right? Because that's got a degree that's smaller on the top than it is down below. So the degree of the top is less than the degree of the bottom. That's actually this case here. So this one would go with this case, which would tell you that you'd have a horizontal asymptote at y equals 0. It would be kind of like that. I mean, the graph doesn't look anything like that, but it has the same horizontal asymptote at y equals 0. At the x-axis, it gets closer and closer and closer. Let me give you a real simple example of this. One that has a degree that's larger up top than down below. And it's this one. F of x is equal to 1 over x. The degree of the top is 0 because there's no frickin' x's. The degree of the bottom is 1. So we have degree 0, and then we got that degree 1 down here. Huh? So that's telling us that we must have a horizontal asymptote at y equals 0. But when we graph it, it's like, well, no shit. We know this graph. This is our hookup. There's our 1 over x. Of course it's got it. It's got your little horizontal asymptote right there at y equals 0. Good to go. Because the degree of the bottom is larger than the degree of the top. So we get y equals 0. Now to go back to what's in blue, let me give you a quick example. Let's say f of x is equal to x squared minus 4 over x plus 2. Okay. The degree of the top is larger than the degree of the bottom, correct? We had a 2 up top, 1 down below. And when you do some fancy algebra to this, you just find out that it's x minus 2 with a hole right there. So really what this graph is, it does this. It's got a make a little hole right there. Boom, and it takes off. There's no horizontal asymptote. That shit blows up to infinity. As x gets bigger, the function gets bigger. How dare you, right? There's no horizontal asymptote there. So when the degree of the top is larger than the degree of the bottom, there's no horizontal asymptote. Now this, again, is an algebra review, which is going to make you just a badass when you start dealing with these limits. Now 1 and 2, these are the silly cases. I don't really like these cases all that much. They're not very interesting for calculus. What's interesting for calculus is when you have the same degree. When we have the same degree. Let's take a look at this. Let me give you an example. Say r of x. So we get 2x squared minus 1 over 3x squared plus. Let me keep it with numbers. Plus 13. Cool. Now, when we have the same degree, top and bottom, what we do is we just isolate. We just look at, all right, take the whole piece along with its coefficient of the largest degree on both of them, and then do this. Now, everything else, you can tell to piss off. Everything smaller than it, it doesn't matter. None of this stuff matters. The negative 1, the positive 13, because when we're talking about a horizontal asymptote, I want you to think that with me. Let's go on a journey. If something here is traveling, what the hell lives way over here? If we continued on this arrow forever, what lives over there? Infinity. As we tend that direction, we go towards infinity. So as our x values get bigger and bigger and bigger. So let's just choose a couple big values, like 2 times something squared over 3 times something squared. Oh, and then minus 1, because that's going to really frickin' matter when I put in 1 trillion. And then we square that shit up. You know, 1's going to matter. And now imagine you go towards infinity, which makes a trillion look like nothing. Because infinity is a concept, not a number. It doesn't, those coefficients are not the coefficients, those are constants. That shit doesn't matter. It wouldn't matter if we just had this. None of that shit matters. As long as it's a smaller degree back behind. So really, when we look at this, if you want to know where it's going to go as x tends towards infinity, where its horizontal asymptote is going to lie, well, shoot, just look at this piece. We'll say it's going to happen right here, and just write this in. What happens to the x squareds? Y equals 2/3. We got some sort of horizontal asymptote right there at 2/3. And I don't know if that's not the graph of it. That's certainly not the graph of it. I've just given you an example. So I just wanted us to be able to know how to find a horizontal asymptote. So when the degree is the same top and bottom, now I'm going to write it out. Oof. Here we go, bud. Here we go. P of x, Q of x. This might get a little bit much, but I want to be technical with you, or kind of technical. So for P of x equal to some ax to the n plus. Oh yeah, you're going to love this shit. You're going to love this.
the first x plus a naught, and then q of x. Don't stress about all the stuff I'm writing right now. I'm just trying to scare you a little bit. You're going to have to know what this shit means eventually. Work up to it. So if those are polynomials on top of each other, we could say, since we have the same degree, both top and bottom, then we can say for certain that our horizontal asymptote is that y equals, and all it is whatever the leading coefficients are. The leading coefficients. And it would be a sub n over b sub n. So there's being a little bit more precise. I didn't put everything in. I didn't put all the bullshit in. But once again, just quick. Let's look at this. 12 minus 15x to the fourth over x squared plus 30x to the fourth plus 1. Where's the horizontal asymptote? Well, actually, first, what's the degree of the top? 4. What's the degree of the bottom? 4. What's the horizontal asymptote? You just take this shit with a sign and everything. Negative 15x to the fourth. And you take this with a sign and everything. You go 30x to the fourth. This shit goes away. Negative 15 over 30. That's negative 1/2. We have a horizontal asymptote there. Knowing this will help you be able to see the problems when we start doing our limits. I'll see you in the next one.